You go. All right, is it coming up? Hey, Reynold, did your slides go up somewhere? Might work. Oh, is it coming up? Oh, wow. Okay. And then I need to add this. Got it. Hopefully I put the right. And then the question is, yeah, you can like walk down around there, but hey, Kurt, could you? Yeah.
I just typed.
Oh,
I can't.
yeah, that's fine. Let's see here.
Can I help with anything?
No. Okay. Okay, I think we're good. Thanks, Scott. You know where this? You stand here. All right, thanks for coming to the Spark Meetup tonight. I'm Andy Konwinski, one of the co-founders of Databricks, and one of the grad students that worked with Mateo early on in the Spark project as he created it back in the Berkeley Temp lab. I've been helping run meetups for Spark since the first meetup, which was, I think, probably 2 years ago. This is maybe something like the 20th meetup, and we're excited to have all of you here. The talk tonight is going to be about a new abstraction that was recently introduced into Spark. Reynold blogged about it this morning, you may have seen, and he'll be telling you all about the details of DataFrames, the new abstraction inside of Spark, a little bit more background about Reynold. Reynold is another one of the co-founders of Databricks. He was also a PhD student in the UC Berkeley AMP lab. He was the lead on the Shark project, which was the original incarnation of SQL on top of Spark. Since then, Databricks and the Spark community have transitioned to an even cooler version of running Spark, or SQL on top of Spark, which we call Spark SQL, as all of you probably know. Reynold's been also key in the Spark SQL work, including the DataFrames work that you'll see tonight. So thanks for joining us. And then for those of you who walked in late, just a minor or maybe major, depending on how hungry you are, logistical note. We unfortunately do not have food at this meetup. We've heard rumors that there's food nearby, and there may be a surplus. So feel free to poke around and find some food. We apologize for that. We did say we would have food on the meetup.com event notification, and then we had just a snafu with the logistics of the venue getting the food to happen. So we do take food very seriously at our meetups, and sincerely apologize. So without further ado, Reynold Xin on the new DataFrame abstraction inside of Spark.
Right. Thanks, Andy, for the introduction. You guys can hear me okay? Yes. Right. So every time we give a talk at this conference center, the very strong lights always shine directly into my eyes. So if I'm not making eye contact with you guys, it's not because I don't love you. I do love you for coming to this event. It's just the lights is keeping me from making too much eye contact. And tonight, I want to talk to you about the data frames. And before I go into sort of the details of the talk, I just want to get a show of hands on how many of you have read my blog post that was went live this morning. Maybe about like a third or close to half. Cool. And how many of you have used Spark, have written like a real Spark program? Almost everybody. Cool. So I'm hoping, so DataFrame is actually designed with a slight audience in mind. I think it will actually make it very interesting for all the existing Spark users as well. So this is actually, I was going back to the slide decks I made in the past couple of years, and I took one slide from 2013, which is not that long ago, but sort of given the rapid pace of development for Spark, it seems like it's been a while. So this one slide from 2013, where as we were introducing Spark, there were sort of two high-level takeaway points in the introduction. One is performance, the other one is usability. And indeed, a lot of early users, actually the very earliest users, probably come to Spark mostly attracted to the claim that Spark is like a lot faster than Hadoop MapReduce. But over time, people are starting to realize it's actually a lot simpler to program Spark because you often ended up with something like this. On your left side is sort of how you write word count using Hadoop MapReduce, and on the right side, you can't really see it, but it's basically using Spark to write the same word count program, which somehow is now the hello world of big data. So probably like, and this doesn't include any of the import statements. So sometimes like hundreds of lines of code can now be reduced to a few lines of code that's actually unit testable and understandable, and that was pretty cool. But as Spark grows, we sort of want to sort of make big data easier and can make the Spark ecosystem actually benefit a wider audience. And I took this morning sort of a snapshot of the Google Trends for the keyword Apache Spark. So one interesting thing is we actually donated the Spark project to the Apache Software Foundation somewhere around here. So July 2013 was when we donated Spark to ASF. So I wasn't sure what people were actually Googling before that July 2013. But anyway, Spark has seen rapid growth, benefiting a lot of the Hadoop users, especially they're very covering from sort of very bleeding edge early adopters. And now a lot of Hadoop users are adopting Spark because of a lot of the Hadoop vendors actually supporting it for the benefits it brings. But I think to sort of truly leverage the power of big data, we need to make Spark and big data actually more accessible to a wider audience, and especially the growing data scientist community. And for this new community, they actually don't understand sort of the functional programming concept very well. They're not training in a paradigm of map and reduce. Sometimes it's hard for them to reason about a MapReduce program. And when they sort of come to the Spark, if Spark API is the second thing you learn to do MapReduce first, and then you learn about Spark. It's tremendously simple to program. However, if Spark API is the first thing you learn, you don't have any functional programming background, you don't know anything about MapReduce, it is sort of a little bit intimidating. For, I think, primarily two reasons. One is majority of the data you process is actually somewhat structured. You might call it semi-structured, but it's mostly structured. For example, JSON data, CSV data, Avro data, Parquet data and Hive, XML even, if anybody's using it. And that, so RDD, the core programming concept in Spark RDD doesn't actually have any schema or structure associated with it. It's just arbitrary plain sort of Java or Scala object or even Python objects. So when you program a typical sort of data pipeline, you inevitably ended up using a lot of tuples, which means your program sort of reads as if this is a bunch of underscore one, underscore two, underscore three. So we're using Scala, we're using Python, it's a bunch of square bracket 0, square bracket 1. And the second thing is functional transformations, as I mentioned earlier, like MapReduce, are not as intuitive for a lot of users, especially those who haven't been trained in the MapReduce paradigm nor functional programming. So now, to get another show of hands, I have 4 lines of code that's written in PySpark. Put it up here. How many of you can tell me what this 4 lines of code does in a few minutes, or maybe 20 seconds? If you figure it out, put up your hand. 1 guy, 2, couple more now. All right. So slowly. All right. Now, that's good. You guys are a lot smarter than I am. So now, how many of you can tell me what this means just by looking at it? What's happening to those that's not putting up their hand? So this is essentially what we're trying to accomplish with this new DataFrame API. We want to move something that's as complicated as what's above, which is already substantially simpler than using a lot of other frameworks, and turn it into something even simpler, so anybody can really understand. So the DataFrames API in Spark, essentially, we're introducing a new concept on top of the RDD API that represents a distributed collection of data that's grouped into named columns. And this is conceptually the same as sort of a table in a relational database or data frames in the various other DataFrame implementations like R or Python Pandas. And on top of this abstraction called DataFrame, excuse me, we have some domain-specific functions available to simplify a lot of the common tasks. So one example is what I've seen here for aggregation. And then the API is actually available in Python, Scala, and Java. They look remarkably similar for both Python and Scala. And this R API also comes via our separate project called Spark Art. They'll be building sort of a distributed data frame concept directly on top of what we're talking about here tonight. And it's actually not just simpler, as those of you who read my blog post. It's more concise, easier to understand. It's actually often ends up being more performant for the reasons I'll talk about in a bit later. But this is just one. I did a very simple experiment on my laptop, just taking 10 million of integer pairs and start running a group by aggregation on it. And one remarkable thing about the DataFrame API is you get the same performance for Python and Java. And then you actually get the same the performance. They'll probably end up being faster than your handwritten Scala or Python code. So because they all get compiled down to the same bytecode execution, which I'll talk about later. So for the remaining of the night, I've already done the introduction in a way, and I actually think the best way to talk about the DataFrame and to introduce the API is just to show you a few examples and demos, because it's fairly self-evident on what it does. And then I'll dive into a little bit more about the internals of how we designed it. So let me switch to can you guys see this okay in the back? Good. All right. So what I have here, for those of you that don't really know what's going on, is it's sort of a Databricks cloud, which is an online platform for doing Spark as a service. And there's a notebook here. It's sort of similar to IPython notebook. And I'll be using this for doing demos. It's a lot easier to set up. So first of all, I want to sort of cover how you can create data frames, and then how you can sort of viewing samples of data out of a distributed data frame. You might have terabytes, even sometimes petabytes of data. You don't want to sort of view all your data at once. And then common operations like filter, aggregation, and joins. And then running sort of user-defined functions. And so last but not least, I'll cover a little bit of Pandas integration. So there are many, many different ways to create a data frame, but there's probably, I categorize them into about 3 categories. The first is you could actually create a data frame based on a table in Hive. So for those of you that's familiar with Spark SQL, the SQL contact is the sort of the central context object for Spark SQL. And you can just call a table function on it, and then pass it the name of the table, and it's going to create your data frame representing the data of this table. So in this case, I have a Spark commits table that I'm running. By the way, it's running Python, just in case you haven't figured it out. So for those of you, actually, how many of you prefer Scala over Python? And how many of you prefer Python over Scala? It's half, maybe half-half. Okay, I'll take Python for now. Right? Otherwise, you have to wait 30 minutes for me to remake it. So once you create a data frame, you can actually there are many different ways to understand more about DataFrame. Like for example, you can call types, which is actually the same method name you used in the Python Pandas DataFrame to understand the schema of the thing. So if you just run dtypes, it's going to print you basically all the columns and the associated data type in the string representation. And what I have here is actually a table I created by not crawling, but using the Git. I generated a table based on all the commit activity in Spark based on Git. So essentially, I just run Git and then I crawl GitHub a lot to dump a bunch of data into this. And I didn't really process the data that much, so everything just strips. So you have like commit hash and all that. As an example, you can actually should see a sample of the data. So in this case, commit is a data frame, and head is what returns you the first 5 elements in here. And displays the data frame, Databricks cloud specific concept. They just visualize the table rather than print it to the console. So what happens here is you have a bunch of data, for example, contains the commit hash, the parent commits hash for those of you that understand Git, and it's like the name committer on the commit, and the email of the guy, when it was committed. Actually, this is the author of the commit, and this is like who actually committed the code. And the email and all of this information, subject of the commit, and the body of the commit messages. So for those of you that prefers more the RDB API, you can also just change head to take, and it'll work. It's basically alias of each other. And then, so I talked about the first way of creating a data frame, which is based on the relational table in Hive. The second way you can create it is by pointing it to data sources, which supports a lot of different file formats I'll talk about later. In this example, I'm just showing something very simple, which is like a very small Twitter data set that's in JSON format, which it turned out actually a lot of the big data sets are in JSON collected somewhere. And you could just call a load function on the SQL context to create a data frame by specifying the path in the data type JSON here. And what actually happens under the hood is, no, I didn't actually specify the schema. So what happens under the hood is Spark SQL or data frames actually goes through the file to infer the schema of the structure. And then, so D types. How many of you have seen a tweet schema? So like 20–30% of you. Yeah. So it's actually going to be very long if I do D types because there's so many fields in tweets. I never understood. I initially thought, how much can a single tweet, 140 characters, take up space? But if you actually type the schema, it would be pretty crazy. So D types will make it slightly incomprehensible. What I'm going to do is a separate function called print schema that prints it nicely in a tree form. So this is what a tweet schema looks like. This coordinates about, I think, it's geospatial elements of where the tweet actually happened. It's when it's created, and there's all kinds of stuff that I can go through. I think we can spend an hour just explaining this. So anyway, this is actually a very useful feature because you can now just point it to files, and in most cases, you can infer the schema for you. In some cases, on formats that actually have self-describing schema like RTO Avro, you just extract the schema out of it. And it was kind of funny, so we had a user using an earlier version of this, pointing at their own log data. And then at some point we realized, oh, we had this kind of data in our logs that didn't even know before from the first schema. So that's the second way, is by pointing the SQL context to files. And the third way of creating a data frame is you could actually create data frames based on RDBs. So this is if you have some sort of RDB that you already created based on your crazy transformation you have with the ETL process. Now you can turn it into a data frame by calling the toDF function. So what I have is here, it's, for those of you, does everybody know what parallelize does? Yeah. Maybe, all right, so what parallelize does is, it just, range 10 is just a simple thing in Python that creates a local collection from 1, I'm not sure if it's 1 to 10 or 0 to 10 or 0 to 10. But I'm actually that big of a Python user. And you can call parallelize on the local collection, and then Spark will create an RDB based on the local collection. This is very useful, mostly for doing testing, and demo. So what I'm doing is I'm creating an RDB of tuples, and there's two elements in the tuple, x that's turned into string, and then x itself, which is integers. And then you can just call 2df on RDB to convert it into a data frame, and by passing in the column. So in this case, I'm creating a key value data frame based on the RDB, and then I can see the content of RDB. So you have key 0. So there are three ways to create data frames. You can create data frames from RDBs. You can create data frames from files. You can create data frames from a relational table in Python. Actually, for those of you that are Scala users, let me cover this. So as expected, you could turn an RDB of case classes or RDB of tuples directly into data frame. The same 2df function exists in Scala through implicit conversions, quite nice. And more than that, you can actually turn the sequence of, without even using SC.parallelize, you can turn the sequence of case classes and sequence of tuples directly into data frames. So in this case, I'm just turning a very simple data frame of 2 elements local sequence. And in this case, I'm defining a case class and I'm turning it into a data frame. So for Pythons, you can turn RDB of tuples, and for Scala, you can turn RDB of tuples and RDB of case classes. So now you created a data frame. You're gonna perform operations on it. So this we define a bunch of operational transformations as I think would fit most of the common data processing workloads. And starting with filter, which is probably what you do almost always. So I had the commits data frame from before. I was tired of typing commits too often, so I give it a short name C. And then there's actually just a dot filter function that you can run in the data frame. And then you could pass the column name in Python as just an attribute on the data frame, and then compare it with, for example, in this case, I'm comparing the author email field of the data frame, and I'm running a filter to filter out everything that's not equal to RXI in the Databricks.com. It's pretty fast. Actually, surprisingly fast. Faster than I did it this morning. So this is pretty easy. For those of you that come from the Pandas background, there's also a Pandas mode that you could just remove the filter and do it with a square bracket, which is exactly what you do in Pandas. You get the same thing. So if you prepare for the Pandas style, you could do it. I personally find having an explicit filter there is more readable. And then, of course, it's not very useful if all you can do is filtering data. You can also project applying to the expressions onto nodes. So in this case, I'm using the commits table, and I'm filtering the author's email and just by my own email address, my own user ID, and then I will select. So just like the projection, to select the date of each commit, and then the title of the commit, essentially. So this tells you at whatever this date needs. Looks like a Unix timestamp. I added a Derby dependency to Maven POM file with the JDBC Java test. So this data is actually not very readable. It's not, like, humans don't really read Unix timestamps. So what you can do here is actually data frames. We made it very easy to define user-defined functions. Even though you could probably convert this with built-in functions into the more proper date, but sometimes you might just prefer your own programming language or the libraries you use. So I'm going to demonstrate how can you actually define a UDF to convert whatever this is into a more proper readable date. So what I have here, I'm just importing a bunch of types that's defined in the Python package DataFrames for SQL. And then I'm creating in 2 UDFs, actually. You can define a UDF by just calling UDF and give it a lambda function or a normal Python function. So I have two UDFs here. One is a UDF that converts the Unix timestamp to actually a date by using the datetime package in Python. And if you remember, every single field was a string. So I'm using a float here to actually turn the string into a floating point number, change it to an int also. And then here tells basically the last argument dictates that the UDFs returns a date type. So this tells the underlying engine more information about the type. And I have a second one which defines hour of day. I'll just come back and get the what. Actually, I'll explain that. What it does is very similar, except instead of converting the Unix timestamp to a day, it's just converting a Unix timestamp to the hour of day. So if it's 0, it means midnight. If it's 1, it means like 1 a.m. And because the Unix timestamp are based on UTC, so I'm actually plus 16 to get to the California time zone, the Pacific time zone, and multiply by 24 just to make sure I can get we only get hour 30. And that returns an integer type. So now we've defined a UDF today. So now I can actually, in the projection, use the UDF directly on the field. And what I'm going to do here is I'm going to alias it by whatever this UDF return, alias it and call it a commit date. Now select the subject also. So it runs pretty fast, and now you have a more readable date. So apparently, about close to 2 years ago, I added this. I don't remember now. So that shows you how easy it is to just define UDFs. If you have used sort of other, sometimes relational databases, sometimes like Pig, you still understand how frustrating it is to have a separate packaging, compilation, packaging, and distribution process for UDFs. Here, everything's in a single program and single script. You just do what I do. And still unit testing. So now, filter, project, aggregations, which is what I showed you from the very beginning. So you could actually run aggregations. This is actually a quick patch I did because I found a bug this morning. I was testing it. So I defined a function to work around the bug. By the time DataFrames actually released, you don't need the same. So what I'm doing here is I'm using the DataFrame and just grouping by the author name, which is doing a count on all the, so by basically you group by the author name and see how many commits each author has generated. And I'm sorting by the count in descending order, just take the top 10. So this is just to see who has committed the most number of commits to Spark since the very, very beginning. So run it. This is like strangely fast for what. So as you can see, the page of Haria, the guy that created Spark, no surprise, he has like over 1,500 commits. And then you have Patrick, who's actually a release manager for a number of Spark versions. That's over 800, and then I actually have about 700 commits. So yeah, you can run aggregation pretty easily. And then aggregation next would be sort of joining. It is actually very common in data science. You can combine sources of data, different sources of data to make decisions. Maybe you want to combine sometimes your user, so your user database with your traffic log, as I've written in my blog post. So join is sort of the operator that can do that. This is what's known as merge in Pandas, for those of you who's curious. So what I'm doing here is I have a separate table that I also collected from Git. That's called Spark Files Change. So I'm getting a data frame from that table, and just to show you what the table looks like. So this the table has only two fields. There's a commit hash and the path of the files changed. So for example, in this commit, which is identified by this hash code, we changed two files, status.py and task result getter.scout. Now, this by itself is not super useful because I don't know when the commit was made. I don't know who made the commit. So what I'm going to do is now I'm going to join the F data frame with the C data frame I created earlier. So if you remember, C data frame has information about each commit, also identified by the commit hash. So it's identified by the commit hash and tells you who are the author, who are the so it's fairly simple to run a join. All you need to do is call join on the data frame, and then join with different data frames C, and you pass it the join condition. In this case, the join condition is just simply an active join on the commit hashes. And then once I've done that, in this case, I'm just trying to see how sort of. So what I'm running here is running a more complicated aggregation that grouped by the path. Essentially, the path is the file. And I'm doing a count distinct on the author name by each file. So essentially, I'm trying to compute how many distinct authors have committed or changed each of the particular file. And I'm aliasing the column authors and sorting by the number. So the most frequently edited file in Spark is actually the build file, spark-build.sky. The second most edited, it's actually the most frequently edited by different authors. There's 86 people that actually edited this file since the beginning of Spark. And then the second one will be Spark context. The 72 authors that actually modified the file. And the third is the Maven build file, Hanta XML. It's over 66 authors. It's very easy to do a join. And then I was playing with dataset, and I was curious about actually my own schedule. And I wasn't sure exactly if there's any changes to my schedule. So I was running a DataFrame query to actually see how often do I go to bed, or how late and how early do I go to bed and wake up. So what I'm doing here is actually very simple. I'm just filtering the author name based on my name, and then just group by the commit hour. In this case, if you remember, I defined an hour of day, Python UDF, to just return me a single integer about hours. And then I'm just counting basically a histogram of my commit activity based on the hours. Use that as a proxy for when I go to bed. So this is a top secret private information that shouldn't leave this room. Let's just run that. So this is essentially the raw data, but it's slightly more readable to turn into a histogram. So as you can see, in midnight California time, I'm actually fairly active. I committed a lot of patches. And then it quickly falls out. So most of the time, I probably go to bed actually around 1 o'clock. And then sometimes it wakes up, gets to work around 8, sometimes 9, sometimes 10 is probably starting to peak. You see there's obvious a lunch break. And then afternoons actually my peak productivity hours. And then it's like afternoon peak week. And then around dinner time, sometimes it drops a little bit, and then after dinner, went up again. So it's, I think, pretty interesting. With a few lines of code, you get to analyze your own behavior based on some public data, which actually everybody can get this data. So last but not least, I want to talk about Pandas integration. So for those that's coming from Python, or you can usually seem to support is coming from Python background, Pandas is actually becoming the de facto, I think, data analysis tool in the Python language, PyData language. It's kind of interesting. So reading tweets this morning about reactions to my blog post, and then I noticed about half of the tweet actually mentioned, oh, this is great, this Pandas integration now. Even though I only had about one sentence out of a paragraph that said, this also works with Pandas. You can 3D convert data frames between Pandas data frames and Spark data frames. But about half of the tweets actually called out the Pandas support. So I decided to make it slightly more prominent in this talk. So you can actually convert, again, 3D between the Pandas data frame and the Spark data frame. It's very easy to convert from the Spark way to Panda. You just call two Pandas functions on the data frame. So by hours is what I defined earlier. Pandas data frame is not distributed. So the caveat is, if you have like terabytes of data, don't call two Pandas. Otherwise, you're going to crash your program. Because no, it just doesn't. I can't define the law of physics to fix that. So and now there's actually a whole world of PyData ecosystem that you can tap into through this. For example, plotting. There's actually great plotting tools on top of Pandas that you can use. So in this case, I'm converting a data frame, which in this case is already quite small because there's only 24 hours in the day in this universe. And you call two Pandas, and you can just plot it. So I'm plotting a histogram here, just using whatever Pandas tool. So here you go, you get a histogram. And you can integrate with a million other Pandas tools. This also means you can use, so the other direction is you can also go from Pandas to a Spark Dataframe just by calling create Dataframe method in the SQL context. So you can just pass a Pandas. Yeah, so the question is can we do this in Scala? Unfortunately, there's no, Pandas doesn't work in Scala, so this would be a Python only feature. We can ask the Pandas email us to do the Scala project also. It might take a few years. But if it's in Scala, you could probably use actually the Spark Dataframe. It's really feature function. So you could do this, and the other direction is going from Pandas to Spark Dataframe, just by calling create Dataframe on the SQL context. Once you do that, it's gonna again take the small data in Pandas and parallelize it if you want. The one interesting thing is that also means you could tap into the PyData ecosystem in the other way, which means, for example, Pandas have excellent support for reading Excel file, which I don't expect it to be on hundreds of megabytes anyway. So you can perfectly find reading in Pandas on a single machine and then convert it directly into a Spark Dataframe. So now you can read Excel files, get excellent support for like CSV and all through Pandas. It's pretty cool. And then one more.
Yeah, so how about the support for like a binary data and the streaming?
I'll come to that again. Actually, I will answer the binary data. I just want to that. So the question is, how about support for like binary data and streaming? So binary data, there's actually a great byte array type in DataFrame. So you could just put binary data that way. When it comes to streaming, in Spark Streaming, you can always, it's like a transform function. They could always pass like RDD transformations in. So DataFrames, I'll talk about it later, but DataFrames essentially gets compiled down into RDD transformations. So you can actually pass that into streaming that way. We are working on or thinking about sort of longer term support for what it means for streaming on DataFrames, because I actually think streaming is one case where you actually want an often head structure, and something like DataFrame for streaming would be very useful for that. But that's in the work.
So for the type of binary data, do the developers need to manually detect? For example, I'll give you a binary, but some library can detect whether this is an image or video, or whether it's JPEG.
You could just call those libraries directly.
Okay.
Yeah. I mean, to DataFrames is opaque bytes, right? And then it's like bytes doesn't mean much, and you can define it in the user level program, and then call whatever library, image processing library you want to call. It's one.
When is going to be released?
1.3 in early March. You can check it out from GitHub, and I have one slide on it. So last but not least, I said last but not least twice, I realized. So the final last but not least, you can actually also run SQL over DataFrames. There are a certain group of data scientists that hate SQL, but there's also, it turned out SQL on our DataFrame is actually one of the most popular packages in R. So we figured, why don't we support it? And actually, as soon as I tell you how DataFrame is implemented, you realize it's no brainer to support it. So essentially, for any DataFrame, you can just register it as a temp table, which essentially creates a temporary table in this session. There's also ways to create a permanent table if you look up the API guide. So what I'm going to do is just create a commits table from the C DataFrame. And then you can run SQL in the command line shell or in the Databricks itself, like prefix of %SQL on it. For example, describe commits is describe the schema of it. It's a bunch of strings. And then you can run, for example, aggregation query on SQL. So if you prefer SQL, here you go. All right. Now let me come back to the second half of the talk. So there's one other thing I wrote about in my blog post that I didn't actually demo here, which is machine learning. Sometimes aggregation and joins are great, but sometimes you want to do something even more sophisticated. You want to predict, for example, how likely a user is going to click something, or what should you recommend to the user. So it turned out the MLlib, the machine learning library on top of Spark, introduced a new API in Spark 1.2, the last release, called the pipeline API, which allows you to sort of make different machine learning modules very composable. And the ML, the pipeline API actually built on top of the earlier incarnation of the DataFrame called Schema RDB, and will be in 1.3, be building on top of DataFrames. Essentially, this is a very simple example that shows you a machine learning pipeline that you construct using the pipeline API in Python. So you have a tokenizer that gets a bunch of text, and then you want to turn the text column into a bunch of words. So this is what the tokenizer does. And then there's a hashing function that hashes the words into sort of some sort of buckets. And then we can run logistic regression on it and construct a pipeline that consists of these 3 stages. And you can just call pipeline.fit on the data frame to actually train the whole pipeline on the input data from this data frame. So this is going to be pretty cool, and a lot of other. So machine learning library is just the beginning. I think every component in Spark in the future will migrate and be building on top of data frames, because this is really the abstraction that makes sense with schema for all this data pipelines. The schema RDB is now renamed DataFrame with a type alias, so it doesn't break your source compatibility. So now I want to talk a little bit more about the design and internals of DataFrames. So it's great to.
So how it's going to look how DataFrames work with where RDB functions?
With what?
Where RDB functions when you have like a key value.
Yeah, how would DataFrames work with pair RDB functions, which is a key value pair, RDB of key value pairs? It largely, in the DataFrame land, because now you have schema, you're no longer forced to use the key and value schema. So you could basically, like for example, you want to run an aggregation or joins, you can just specify the column. You don't actually need to run the key value. You don't have to like force yourself to think in terms of key value anymore. Think about you have columns. I want to join these 2 columns together. I want to aggregate on this column. So it actually makes it probably easier and you don't have to think about it.
So where RDB will go?
No, it won't go away. It's the API is still there. So I mean, there are its uses, right? You could run. Sometimes people just prefer that. Okay, so I want to talk a little bit more about the internals, and really, we've been working on this for the past few months, and I want to share with you some of the thoughts on designing this API. And really, it comes down to wanting to make simple tasks really easy for users and still make very complicated or sophisticated tasks possible. In the simple task easy part, I've shown you sort of the DSL or the functions for transforming data frames. It's very easy to both understand and write. And then we have done a bunch of things to actually make it easier, so we don't have to worry about a lot of the nitty-gritty details. Like, for example, you want to define schemas. And then there's even sort of machine learning integration on top of it. And the complex task possible is actually each data frame under the hood can be viewed as an RDB of row, or in the case of Python, RDB of tuples, mean tuples. So you can actually apply all your favorite RDB API like map, reduce on it to write arbitrarily complicated programs, including the pair RDB functions. And there's actually a full expression library that I didn't cover about tonight. You can apply transformations even more complicated than what you can do in Pandas. And then compare with a lot of the existing data frame implementations. This is designed with big data performance in mind. So there's a lot of things we are doing that I'll talk about in a bit. And last but not least, it is made to be sort of integrated extremely well with the big data ecosystem, including supporting a lot of the common data formats and data sources, as well as interoperable with different data systems like Pandas are. It's the question.
You use the triple as an analogy for
DataFrames actually don't. The question is.
Sure. The question is simply, you know, we made an analogy that the data frames are like an RDD of tuples. There's no 22 limitation like tuple size.
It's actually RDD of rows in Scala, so there's no limit of 22. In Python, it's RDD of tuples. So internally, a data frame is actually represented as a logical plan. For those of you that understand more about relational databases, it is essentially a logical plan in Spark SQL. The execution is lazy, similar to RDDs, which means we can actually optimize a logical plan generated by a data frame. And it's actually easier to optimize, and we can optimize it better than usually the vanilla RDD operations, because data frames provide more information, including schema and the expressions, to the underlying engine. So essentially what happens is, in the case of Spark SQL, you have a SQL query, and the SQL query gets parsed by a parser and turned into a logical plan. In the case of data frames, it's actually just a programmable way of generating logical plans. So when you actually want to execute a data frame, run some action on a data frame, it's passing through the Catalyst optimizer, which is the same optimizer used in Spark SQL for running optimizations. And eventually, everything gets compiled down into RDB transformations under the hood. So essentially, data frames are sitting on top of RDB transformations under the hood. As an example, let me just show you. So what I have here is a very simple data frame transformation that selects two fields and running a filter. Right? And then you can actually call explain on it. In this case, I turn extended information. And you get a whole, this is like the parse plan. Essentially, you have a filter on top of a project, on top of a subquery, on top of in-memory relations. So everything actually for this data is in memory. And then you can see what happens. For those of you who are familiar with Spark SQL, this is essentially the analyze plan, which means there's an analyzer that goes through the plan to make sure everything is valid and figure out the data type and the resolution of attributes and all that. And then you can see the optimized logical plan, which applies logical optimizations to the plan. And then eventually there's a filter, the physical plan, which is actually quite simple. It just runs the filter on the scan. So data frame executions actually compiled by the, or optimized and compiled by the Catalyst optimizer down into physical plan execution in terms of RDD transformations. So this actually is very powerful because compared with a lot of the traditional data frame implementations like R and Pandas, they are very eager, which means every time you run, for example, a filter or a project or a join, operations happen immediately. I think in the case of small data, where most transformations take in a matter of maybe a second or two, is perfectly reasonable. But when you have to deal sometimes with big data, that can actually be particularly expensive. So just to show you one example, let's say I'm running this join. I have a user's data frame. I'm joining with some events log I have. And I'm just matching the user ID based on the user ID in the event. User ID in the events. And then I perform a filter. This is like just how I wrote the program, because I didn't think much about optimizations, how I can make it faster. I tested on small sample data sets, perfectly fine, runs in a second or two. But what happens here is the plan is you run a join first based on 2 scans, and then you run the filter. In the case of Pandas or R, or pretty much any other data frame implementations out there, what's going to happen is you're going to run a scan on users, which loads every single user into memory. And then you're going to run a scan on events, which loads every events data into memory. And then you run a join, and then you apply the filter. So this join is actually very expensive, because imagine your data log might be a year, over the course of a year or 2, even 10 years sometimes, and it can be very big. And the join requires usually either sorting data or building a hash table of the events data. And you can, in almost all cases, in other DataFrame implementations, you run out of memory. Or if you don't run out of memory, you're very, very slow. Now, what happens in the Spark Dataframe is actually Catalyst will optimize this plan using a lot of the traditional database optimization techniques to push the filter down into the scan. So now you will read the events one by one in and applying the filters immediately before you do the join. And then now the join is actually only performed on the events that's actually later than January 1st, 2015. So you're actually substantially reducing the amount of work you have to do on the join. So there are a lot of optimization that's being done. And the other thing that's actually fairly important for the big data ecosystem is data sources support. As I said earlier, you often want to combine data in different sources or formats as you're analyzing and building data pipelines. And DataFrame support a lot of sources. You could actually, there's quite a big number of built-in data sources like Parquet, can support JSON. There's a JDBC data source. You can connect all the everything that supports JDBC, SQL or JDBC. You can load anything that can be wrapped in Hive and different file systems and all of that. And then there's an external third-party data source API that you can use to define data sources for both DataFrame and Spark SQL. And now we're already seeing external data sources from like Avro, CSV, this thing called DBase, which is a geographic database, and HBase, Elasticsearch, and all this. What's interesting is actually the data source API is actually more than just naive scans, because you'll be, as I said earlier, sometimes naive scans can be very expensive. For example, you have to scan all the events into memory. You can run out of memory. The data source API, actually, the Catalyst optimizer can push predicates and column pruning down into the data source API if the data source can support it. So, for example, in the case of Parquet, you can actually skip columns because Parquet is a columnar format, and you can skip whole blocks of data based on the coarse grain index in Parquet. And for comparisons such as string comparisons, if the string is dictionary encoded, you can actually turn string comparisons into dictionary encoded or integer comparison through a dictionary encoding. In the case of JDBC, we do some sort of federated query processing where you can actually rewrite the query used to query the external data by pushing down a predicate into the query. So as one more, just going back to the same example, in this plan I showed the joins, the events, and users, and we apply a filter. So the optimized plan I mentioned earlier is you can run the filter on scan. But if you're running this for most data sources that support actually some sort of predicate pushdown, for example, any Hive data sources that actually support partition tables, you can actually turn the optimized plan, and you can actually further optimize the plan to create one that runs a filter scan that actually skips almost all the data based on dates, especially when your whole data set is partitioned by date. So just to conclude, DataFrames in Spark, you see APIs in Python, Java, and Scala out of the box. And you see also API for R coming through a separate project on Spark R. We're hoping this will make it substantially easier to consume big data, do big data processing for all of the new users, as well as for existing users. This should be able to make a lot of your existing Spark programs easier to write and easier to understand. And at the same time, most likely improve performance. It will be released as part of Spark 1.3, which is going through so community testing right now. It should be, I think we should have a release candidate anytime now. We officially release in early March. And our vision for this is really, this graph's kind of weird, but our vision for this is there's a Spark Common Core engine which provides RDB API. There's different components that you're building on top of it. A lot of components will also be building on top of DataFrame. But DataFrame is also viewed as the thing that sits on top of all of them. That should be able to give you sort of SQL-like functionality, should be able to eventually give you a streaming-like functionality, and you can run machine learning algorithms all through this single easy-to-use API. So that concludes my talk. I can take a few more questions.
The question is related to DataFrame versus RDD.
Yeah.
One side, you mentioned that DataFrames under hood runs RDDs. On the other note, you have shown a slide of the performances comparing RDDs. In the very beginning, you mentioned for 10 million integer sort this one. You compared the performance of RDDs with the DataFrame. So where do you got that particular performance gain?
It's a very good question. So what happens is now data frames are compiled eventually down to RDD transformations, which means if you're really good at it, if you really want to, you can optimize the hell out of the RDD program to basically handwrite the same code. This is similar to like C++ compilation. You write assembly code that would probably give you some sort of GCC with optimization level 3 turned on performance. But most likely when you're writing, you don't think about alignments, you don't think about, in this case, you'll be creating, don't allocate as many objects. For example, in data frames, because eventually turn into, the time we generate for data frames doesn't actually allocate anything. Essentially just reuses the tuples as you go through. And by tuples here, I don't mean scale tuples, just whatever we have in front of it. So it doesn't do object allocation, and it can push, for example, something down better than usually the handwritten program. So it is true, you could actually write a handwritten program to achieve the same performance in Scala or Java, not Python. It's Python, you just can't beat the JVM. But it is going to be very hard. And the way I got this was I essentially I wrote what a normal user would write for running aggregation. I didn't spend, I could make it 10 times longer to optimize, but I didn't do it.
When moving to the data frames, has anything changed in terms of optimization, shuffling and staging, apart from the curate plan optimization?
Anything changed for shuffling? They are actually the same, actually. So the one nice thing is we are making shuffle more explicit in data frames as well as Parse. So the explicit way one explain on the data frame is actually explicit operator called exchange, which essentially does a shuffle. So we make very obvious in the boundary. But I mean, at the end of the day, it is compiled down to RDD transformation. So all your RDD knowledge and optimization knowledge you can apply them to.
Thank you. So your schema supports nested data structures. Can you show us a little bit more about how you actually access that using the data frame?
Yeah, I need to look up the API doc.
Okay.
It is, there's a bunch of UDFs that you can, not UDF, like built-in functions that you can use to apply. I think one is just called, you could just call like get item to get a position out of it. Out of an array, and then there's get field out of this, so nested struct field. And in the case of Python, I think we just call it that. That's the attribute. Yeah, but it's pretty much it. Thanks.
So what happens if you don't have the statistics in the tables, and how do you generate the plan?
Well, without statistics, actually, everything I've done, I didn't have any statistics. They're always fallback, so you can do right. For most of the stuff, for example, even what I've shown here, you don't need any statistics because it's always better to push the filter down. It's always.
For example, when you join, you want to know which table is bigger. You don't join tiny small tables.
Yeah. When there's no statistics, you have to make some assumptions. Like you usually end up making an assumption that's more robust against sort of incorrect assumptions, right? Like for example, you don't choose to broadcast when you know absolutely nothing about your data.
Yeah, so in that note, can in the coming release, can the user interface optimizer here or something to?
Yeah, it's interesting. Not yet.
Okay. I think I'll be good for that.
It'll be interesting.
Yeah.
Yeah, I don't think we allow you to do things. There are various ways right now that you could technically work around some of the stuff. Like for example, if the data is created from a local data source, it can be assumed that you fit in memory, so you can run broadcast runs. But there's no general things here. Yeah, it'll be interesting to think about how we can add things. Yeah, which actually should be pretty easy because you just add an extra argument to the functions, like broadcast the right side.
Yeah, basically I have two questions. The first one is related to previous one. Is that do you have a host base already optimized for in the product? Because I saw from one of the tree graph path shows customer automatic selection. So we have second question is do we have claims for integrity constraint on the
So the first question is cost-based optimizer. So it depends on how you define cost-based optimizer. Some optimization actually leverages cost. For example, choosing to broadcast or not. In general, there's no joint reordering cost-based optimization yet. Wouldn't be too hard to add, but just don't have it. The second is integrity constraints. I don't think it's very common in data frames in general for integrity constraints. Maybe more when it comes to like SQL. But, there's no plan for integrity constraints.
When you were showing the use-defined functions, and it was a relatively simple function, but are those, I guess, are they parsed apart and made into a format that can be run in a distributed fashion or pushed down into the scan or something like that, or are they essentially opaque? And I guess that would mean you have to run locally.
So I mean, the definition of a UDF is essentially it's opaque to the engine. So this would be opaque. It doesn't mean it has to be run locally, because what happens here is this UDF is actually embarrassing in parallel. It runs on each tuple, so you can actually run it distributed. And then you can also define. I didn't show this here, but data frames essentially can be viewed, as I said earlier, as an RDB. So you could actually run something like this. See, like subject files. I would just substring 0 string. I think there's substring Python. Anybody else? I would just slice it like this with colons. All right. Okay. So you can actually run an RDB operation. For example, here I'm running a map. And you can run like reduce and any other RDB operations on this data frame. And so essentially this way you can also arbitrarily parallelize your program. In this case, I'm running something really simple. Just take the first 10 elements. You could apply arbitrary.
One or two more questions?
Hi, so what kind of drawing is going to support, like a hash drawing or like a merge, sort of merge drawing?
I mean, this is the nice part about sort of this whole thing is you specify just the drawing, and over time, as the engine gets to become, so right now it's only hash drawing actually. This broadcast hash drawing and then over time, as the engine gets smarter and it's more physical planning or physical operating implementations, you can actually choose between the different ones. Like for example, there's already a pull request opening, adding sort of improving dimensional joints, which means we have a large fact table with a lot of small dimensional tables. You optimize your hash map in a way that's actually substantially faster than general hash join. So with every Spark release, your DataFrame program will probably get faster and faster.
I think you probably answered this one. I want to ask a question.
I thought you were going to call it again.
No, I'm going to be the second to last question, actually. This isn't going to be 1.3?
1.3.
And what's the timeline on that? And is it going to be stable at 1.3 so the API won't change?
So we're cutting the release, this is a very good question. We're cutting the release candidate for 1.3, I think, any moment, which means everything should be stabilizing. Only critical bug fixes can go in after the release candidate is cut. It is pretty safe to just go to GitHub and build from source, especially if you want to play with method. So you can just check it out, run it on a local single laptop.
And so will it be in like an experimental or alpha like state officially?
So initially it will be as an experimental API because even though we spent a lot of thoughts into this and we try just writing a lot of programs based on it, we're not 100% sure we have get every single function designed right now. So it's going to be experimental API, which means there's no official guarantee for sort of backward source and binary compatibility. Even though we'll strive to make sure we don't just randomly change it. But if it's something we found later on it's horribly broken, we'll probably have to actually break the compatibility in order to design a better API. So we'll probably stay experimental for at least one more Spark release, which means either in 1.4 or 1.4 or 1.5, we become a stable API.
Okay, last question.
So my question is related to schema inference for JSON files. Do you infer a super schema which every tuple can fit, and if that tuple doesn't have like attribute, you just put null there, or do you missing is interpreted as null, something like this?
We essentially you find the strictest common type that can fit everything.
So if that tuple doesn't have that,
it doesn't have everything.
You just know. Okay. So and my second question is, does that handle heterogeneity in tuples? For example, a column name can have different types. Yes. So what's the behavior when you do group by or join?
Yeah. Eventually, the widest type is string. Okay. So you could, I mean, just in case of JSON, the widest type is string. You can actually parse everything into string.
I see. So there's, always, you don't have typing. You always go to that ending type, which is a string.
Yeah, if you have, schema, if you have heterogeneous schema in general, I think it's impossible problem to fix. There's no way you can actually solve that problem.
So,
I actually have talked to Michael about this the other day, and I'm pretty sure he said that there is a little bit of intelligence that, like, for instance, if there is some attempt to merge the two types.
Yeah, that's what
I
was referring to in the beginning. It's finding the narrowest common type of heterogeneous things.
So it doesn't always go to string, right? But it will fall back to the worst case to string.
If you have an int, if you have a long, it goes to a long. If you have like a double and a long, it becomes a double. But the widest one is string.
All right, let's thank Reynold for this talk. And thanks all of you for coming. This was our Spark Meetup attached to Strata plus Hadoop World. And just a quick announcement, community-related announcement. We are in the midst of organizing the Spark Summit in New York, and the tickets are selling fast. So that will be next month. And we are also working hard to get the program committee voting on talks for the Spark Summit that will happen this summer in San Francisco. And so you can go to the Spark website and get an eye on when that will be and put it in your calendar if you're interested in coming to that. Help us, if you are enthusiastic about the community like we are, help us spread the word about the New York event. We have a lot of coverage into the tech scene and the sort of big data scene in the Bay Area. We have a lot less penetration into the various circles and meetup scene. out there, though it's going really well so far. Ticket sales and stuff. If you know people that are interested in Spark, we'll be in their neighborhood in New York, and let them know about the event. All right, thanks for coming, and enjoy Strata. And we will, Reynold, you're going to be giving a talk, a similar talk.
No, it's
the
a
same
completely
talk.
different talk, actually. It's a completely different talk I'm giving in Strata on Thursday on large-scale Spark workloads.
Oh, right. So see Reynold again on Thursday, and you'll see other Spark talks all over Strata. Thanks for coming.